All right, we're taking a look now at problem 5 on worksheet 2. It says a low friction lab cart of mass 1 kilogram is at rest and has a spring plunger compressed and locked into place. Let me show you what that looks like. Here I have this cute little lab cart, right? And it's got these little wheels on the bottom that when you spin them, spin and spin and spin and spin. They're really nice low friction, okay, lab cart. But more importantly here, this one has this spring-loaded plunger. Okay, there's a little spring in here. I can compress the spring and push this button to click, lock it into place. And then if I press the second little button here on top, that plunger pops out, okay? So click, lock it in place, pops it out, okay? So that's it. So I've got that spring compressed, okay? So here we go. Can I get this to, not easily. I got that guy clamped in there good. Oh, I can just do this. Okay. Hey, look. There we go. Okay, so I've got that. This is the spring-loaded plunger on this cart. Okay, I've got a second cart now. Okay, and it says there's 24 joules of elastic potential energy stored up in that spring. And it says a second similar cart, but this one has a mass of 3 kilograms. See, I added some extra mass on top of it. Okay, 3 kilograms is gone ahead and brought up next to the first cart. Okay, when I release the trigger, right, that spring is going to pop out, and these guys are going to push apart from each other, right? Okay, trigger's released, 2 carts are pushed apart. Find the final velocities for both carts. Okay, so that is the idea. All right. Okay. All right. So you say, yeah, we can do this. Okay, we can do this. Let's go ahead and do our sketch, right? So we'll have our before picture, right? There's the first cart, right? With its spring all compressed, okay, in there, yeah. Okay, here's the second cart. We should be like right up against it, but what are you gonna do? Okay, this cart has extra mass loaded on it, right? We're gonna say that, let's see here, this, want to call this A and B? Sure, cart A, cart B. Cart A, they tell us that the mass of A is 1 kilogram and the mass of B is 3 kilograms. We know that there's, in that spring, there's elastic potential energy, 24 joules stored up. Okay, and they start off at rest next to each other. When we release the spring, they're going to spring apart. We want to find the final velocities. There's our before picture. Hey, let's choose to call to the right positive. Sound good? Sure, we'll call it the right positive. Afterwards, we know they're going to push apart. And I'll have that spring cart. Okay, with that spring now no longer compressed. Okay, that's going to get pushed backwards. This is that final velocity for A, right? Cart B, with that extra mass on top, you say it's going to be cruising away that way. Velocity of B fun. All right, and that's the idea. That's the idea. Okay, so having this set up, you might ask, okay, we're going to do, say, I know that this is an interaction between two things, and you say, we're going to use conservation of momentum for this, but they also give us some energy here. We're going to end up using conservation of energy and conservation of momentum, both of them together, to solve this problem. Okay, it's a good problem. So here we go. Which one do you want to start with? Energy or momentum? Okay, it's the momentum unit, so why don't we start with that? Okay. If I do the momentum, you say, I'm going to say, hey, what's my system going to be? And basically, we're going to say everything, right? Okay, let's include both. We don't know how big the force is from this, so I'm not going to be able to do an impulse. We don't know the duration of the push. We need to include all of this in our system, so that's a force inside the system. So our system is going to be cart A, including the spring, right? And cart B. Okay. When I do that, F delta T is delta P. Okay. hey, what horizontal forces are we going to have changing our horizontal momenta? And you say, well, the force from the spring between the carts, that's inside the system. The only thing they're interacting with is that horizontally, you say, is that track. But we're saying these are low friction carts, so we're going to ignore friction. So then there is no outside impulse. Hooray! So that means the starting momentum and the end momentum will be the same. Momentum is conserved. So we're going to have the change in momentum for cart A and the change in momentum for cart B. You say, hey, that'll be momentum of A final minus momentum of A initial plus the momentum of B final minus momentum of B initial. Always final minus initial for deltas. You say, hey, are any of these zero? You say, yeah, they started off at rest. The starting speed was zero for everything, right? And so that starting momenta will drop out. So I'm getting an equation of just those two momenta, the final of A and the final of B. They add up to zero. They're going to have to be equal but opposite to add to zero. You say, okay, that's what we anticipated. Total is zero. They spring apart. These have to add up to the starting with zero. So equal and opposite. Plugging in to my equation, T is mv. This is going to be the mass of A, the v of A final, plus the mass of B, velocity of B final. And you say, hey, I know the masses, 1 kilogram, 3 kilograms, but I don't know these velocities. In fact, those two velocities, that's what we're trying to find. So good. It's good we got an equation with the things we're trying to find. The problem is, two unknowns in one equation. I need another equation with them to solve. I'm going to get that equation from energy. So now we're going to do an energy calculation. Our system, again, we really don't want outside forces doing work if we can help it. We're going to use A and B and the spring again. So you'd say our work energy theorem, sigma W, is delta K. Because we're including the spring, we can have a delta U elastic. All right? I don't have any outside forces acting, right? So I'm not going to have any work terms. Okay? I'm sorry, let me rephrase that. Outside forces, there's a gravitational force from the Earth and a normal force from the track. Those are perpendicular to the motions we have, so they're going to do no work. Sorry, that's what I need to point out. So what I'm left with here, now kinetic energy changes. I actually have two parts to my system that are moving, right? So I'm actually going to have two delta Ks, all right? Delta K for A and delta K for B. Hope you didn't mind me squeezing that in there. So this will be, expanding out the deltas, I'll have Ka final minus Ka initial plus kinetic energy of cart B final minus kinetic energy of cart B initial. And in the delta UE, that'll be a U elastic final minus a U elastic initial. Are any of these terms going to be zero? And you say, absolutely. At the start, everything was sitting still. We didn't have any kinetic energy at the start. Yep. Starting kinetic energy of two carts is zero. And at the end, the spring isn't crushed anymore. There's no energy stored up in the spring anymore. U elastic final drops out. I just have these three terms. Okay? So my work energy theorem showing only the non-zero terms is going to be, oh sure, we'll write it in real quick here. Ooh. Kinetic energy of A at the end plus kinetic energy of B at the end minus elastic potential energy at the start in the spring. And so that just makes sense. I'm going to lose that elastic energy I had in the spring at the start. It's going to turn into the kinetic energy of the two carts. Okay? At this point, we can substitute in our equations for kinetic energy and elastic potential energy, okay? Which we know kinetic energy is 1/2 mass times the speed squared. Right? 1/2 mass times the final velocity squared. And then elastic potential energy, like, oh, I could plug in the equation for elastic potential energy, 1/2 kx squared. But I don't need to. They told me that UE was 24. I have that value. There's no need to sub in an equation for it. All right? So that's it. Hey, at this point, I know the masses of the carts, 1 kilogram, 3 kilograms. I know the elastic energy at the start, 24. But I got two unknowns here. The final velocity of cart B and the final velocity of cart A. But those are the two things I'm trying to find. Those are the same two unknowns as here. So now I have two equations with two unknowns. I can sub and solve that system of equations. And that's the physics done, right? All that's left now is to do the algebra, right? Okay, so let's go ahead and do that. Do you want to plug your values in right now or rearrange with variables and sub in first? Let's just put the values in this time. All right. I feel like I'm getting a little bit easier on this as we get towards the end of the school year. But anyway, here we go. If I do this here, I'm going to get 0 is, mass of A is just 1 times the velocity of A at the end, plus the mass of B, which is 3, times the velocity of B at the end. So from this, I'm just going to get that, what do you say, velocity of A is -3 VB. Yeah? Okay. I could take this and I could substitute this in where I see velocity of A over here. Okay? I am running out of room. Yep, I'm running out of room. But that's what I'm going to do. Okay, so we'll do that substitution here. Am I really going to try to squeeze this in here? That's crazy, Dave. That's crazy. You know what I'm going to have to do? I'm going to have to erase and give myself some room up top. Sorry about that. I'm going to transfer this line up to the top here. Okay. 1/2 mass of A. And where it says velocity of A final, I'm going to put in this. -3 velocity of B final. And then don't forget, this is squared in the kinetic energy equation, right? So that's going to be squared. Okay? And then I have the plus 1/2 MVB final. You know, I meant to be putting my values in. Oh well. Okay, that's okay. That's okay. That's all right. You don't mind. Minus U elastic initial. Okay. Sorry, I put the mass in here, but I didn't put the mass in there, whatever. Okay, we can put our values in here now. Sorry about that. Let's put all our values in. 1/2 times 1 times -3 VB squared. That's going to be, -3 times -3 would be just 9 VB final squared. Okay, over here I've got a 1/2, mass of B is 3, velocity of B final squared, and then that U elastic was 24. Okay, I've got an equation now with just one unknown, VB final, okay, which happens to be squared. We can go ahead and say, this is 1/2 of 9, that's 4.5. 1/2 of 3, that's 1.5. 4.5 plus 1.5 would be 6. So this is just 6 VB final squared, and then minus 24. Move the 24 to the other side. Okay, add that over there. Divide by 6. 4 is VB final squared. You're like, oh, what's my answer? VB final. You see, now hang on a second. When I take a square root, right? So I take a square root of both sides, yeah? Remember, my answer could be plus or minus. Okay, so it's plus or minus 2 meters per second. Which one do I want? Well, looking at the picture, which I erased, when they push apart, VB's going to the right. I want the positive answer. Okay? Now I know that VB is positive 2. I can come back here, plug in the positive 2 there. The velocity of A final is going to be -3 times positive 2 is going to be -6 meters per second. Do I want that negative? Yeah, A is going in the negative direction. That makes sense. Ta-da! Got to be careful. In the kinetic energy equation, these are just speeds. So like the plus and the minus, you know, doesn't show up. All right? You got to be thinking about it logically through from the system. Okay, plus or minus for direction does show up in the momentum equation. So you got to be a little careful about that, about assigning your signs for directions. Because kinetic energy doesn't have direction. Okay, yeah, that's it. Now you notice the cart with the spring ended up going -6. It had a speed of 6, right, in the negative direction. Speed of 6. The big cart without the spring had a velocity that was 1/3 as big. It had a velocity of 1/3 as big, but the mass was 3 times as big. So the momenta were still equal and opposite. Cart B, 3 times the mass, 1/3 the velocity. Check it out. Doot, 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 doot. Here we go. I'm going to go ahead, I'm going to hit that little trigger button. We'll see how well this works. 3, 2, 1. Could you tell? This guy went considerably faster than this guy, yeah? Okay, should have been 3 times the speed. All right, and that is that. That, my friends, was problem 5.